very happy to present today's speaker, Yara Yakoub. She's a PhD candidate with Dr. Sylvia Villeneuve. She recently returned from Sweden, where she worked with Nick Ashton and Henry Zetterberg. She's also really active in the Alzheimer's Association as an ISTART member, ambassador, sorry.
I was, yeah.
PIA, neuroimaging,
PIA.
Yeah, overall, just a very lovely and supportive lab member.
Oh, thank you.
So, thank you for being here today.
Well, thanks for being here, and thank you, everyone. So today I will be presenting blood biomarkers, based biomarkers in Alzheimer's disease. This is my, most of the work presented here is from my PhD thesis. And I will begin with a brief overview on the history of Alzheimer's disease, how we started, where we are now, and the recent progress in blood biomarkers development. After that, I will walk you through the current projects on how we do prognostic. We use blood biomarkers in prognostic as a prognostic utility, and the longitudinal changes over time across different platforms currently used. And to wrap up, I will address some of the limitations and challenges in blood biomarkers. Let's start with the brief history of AD. So it all started with Alois Alzheimer's back in the 1900s. He was a psychiatrist, studied a woman with memory loss, and later found there was an amyloid plaques and tangles in her brain, which are key features of the disease. Almost 80 years later, from research, they found there was the initial recommendation came out from the National Institute of Stroke and Alzheimer's Disease and Dementia. And this was the first diagnostic criteria or formal diagnostic criteria in 1984 that remained unchanged for over 27 years. And based on this criteria, we can define AD as a clinical entity. So it was based on memory impairments and cognitive dysfunction. Neuroimaging was based solely at that time on large research institutions, and there was no solid research on biomarkers, on biofluid biomarkers. 3 decades later, data has shown that there is an extensive AD pathology that can exist without symptoms. So someone could show no symptoms, completely cognitively healthy individual, but have some extensive pathology in their brain. And this shift was driven by the development of amyloid PET tracers. The first tracer came out in 2004 from Pittsburgh, and later on the tau tracers. And this actually helped us recognize the presence of these pathologies in the brain without even showing cognitive symptoms. And the stage, we started to characterize individuals on different stages and AD as a spectrum, starting from the preclinical stage where we see amyloid accumulation and some synaptic dysfunction, although there is a maintenance of the integrity of the brain structure. And this stage is known as the asymptomatic or the preclinical stage of the disease. Brain amyloid accumulation is necessarily, but is not sufficient to produce the clinical symptoms that is seen in individuals with mild cognitive impairment. So that needed tau, and tau pathology began to accumulate in the brain. There is some type of neuronal loss as well. And cognitive dysfunction, cognitive impairment, but such as thinking difficulties, but these impairments do not affect a person's daily activities. As the disease progresses, symptoms become more and more severe, and individuals lose the ability to respond to their environment, and the stage is known as the dementia stage. This shift in the way we diagnose AD from being a clinical syndrome to as a biological construct has also shifted the guidelines and updated the guidelines from the Alzheimer's Association and the National Institute to use imaging biomarkers. So here we see amyloid PET scan, positive amyloid PET scan, and on the right we have the amyloid PET negative scan of an individual. And then we also look at tau. So this stratification using tau positive scan, and then on the right we see the tau PET negative scan. And neuronal loss characterized by, could be measured by gray matter atrophy or hippocampal volume loss. And here we see an AD patient as compared to someone who's cognitively normal. As we move forward towards defining AD as more biological construct, and the shift in the way we diagnose AD from also using imaging, but also using CSF or cerebrospinal fluid using spinal tap. Spinal tap is actually, it started all before even imaging biomarkers were apparent, but there was some limited development in the technologies and the sensitivity of these technology that could measure these protein concentrations in the CSF. And after around 2011, we were able to measure CSF, or the amyloid and tau and neurodegeneration, using different CSF biomarkers, such as amyloid A-beta 42 to 40, plasma phosphorylated tau 17 and 191. I will walk you through on this later. And neurodegeneration, such as neurofilament light chain. So this progress in the biomarker development also allowed us to do some progress in the drug development. So we do drugs that were available in 2024, lecanemab and donanemab, and they gained approval from the FDA, still under review in Canada. And this brought some optimism and promising results on effective drugs that could target some of the soluble forms of the pathology in the early stages of the disease. So, as we've seen, these drugs like lecanemab and donanemab, and with the progress of these drug development, has been closely accompanied by the advancement of the different technologies that we could use in biomarkers in identification of these protein pathology. And this has led to major shift of focus from the CSF to the blood. But why blood biomarkers? Why this sudden shift in targeting protein pathologies, or these soluble protein pathologies in the blood rather than CSF or imaging? And one of the main reasons is that blood is more accessible and there's more feasibility compared to PET scan. So this is a Canadian map showing here that all the available PET and CT centers, and there are, in 2022, there was around 47 centers. Most of these were very much localized, actually half of them in Quebec and Ontario. Blood biomarkers are also cost effective. So this is a hypothetical model on the cost estimates that are involved in different screening strategies that we use in AD drug development. And the first approach here, the traditional approach, where we do initial phone visit, then screening, physical examination, neuropsychological testing, and then we do amyloid PET scan, and that can cost up to $3 million. The second approach is we start to incorporate blood biomarkers in screening. But first, we do the initial phone call, the screening visit, and then the blood test afterwards, followed by amyloid PET scan. Kind of reduce the cost, not that much. The third and the fourth approach, where we use blood biomarkers in screening before even doing the neuropsychological testing, and the fourth one, even without doing amyloid PET. And this here we see actually there's almost like 1 million reduction in the cost between the fourth and the traditional approach when we don't use blood biomarkers. It's multiplex, so we can test multiple proteins beyond amyloid and tau. So here we see we can test neurodegeneration, and this is characterized by neurofilament light chain that could be measured in the CSF and blood. We can measure some indicative proteins of astroglial activity or neuroinflammation, such as glial acidic protein, or GFAP, with the blood biomarkers. It's also less invasive compared to CSF or spinal tap, which is not very much favored here in patients in North America. And numerous studies have examined how these plasma biomarkers could actually be used or could be correlated with PET imaging, which are considered the gold standard for in vivo for diagnosing living humans, and the CSF. And this is the first paper from 2016 that came out from the group in Sweden, measuring plasma amyloid A-beta 42 to 40. And here we use the ratio just to compensate for the inter-individual variability using single molecular assay technology. And here we see two plots looking at the correlation between the CSF, what we measure with the CSF, and the plasma and amyloid PET. We do see some correlation, yet it's not great, and the assay was not very sensitive, very much sensitive enough to detect these low concentrations of the amyloid. 2 years later, actually a few years later, Randy Bateman group from WashU came with a new assay that's called the mass spectrometry assay, which is known to be more selective and more specific to the protein concentrations and able to detect these proteins at a very much lower concentration. And here we see actually a very much a better correlation and a higher diagnostic accuracy in the mass spectrometry measure opposed to the single or the Simoa technique. Plasma A-beta ratio has been proven to be valuable in identifying amyloid pathology, but what about tau? Tau is the most interesting biomarker, and we were able to detect tau in different epitopes, or forms. So this is a tau protein, and here we see in the protein-rich region we could measure different p-tau epitope in the hyperphosphorylation regions, such as p-tau 231. 217 and 181. And for the sake of presentation, I will just focus on p-tau 217. So this paper came out in 2020. It's actually the first paper that looked at whether plasma p-tau 217 is able to distinguish between AD and other type of neurodegenerative diseases. Is it specific enough for AD screening? And here we see different box plots showing individuals on the AD spectrum where there is a stepwise increase in individuals with increased amyloid and tau pathology. And then compared to other neurodegenerative diseases, such as where we see very much lower concentrations, such as vascular dementia, Parkinson's, and FTD. So this kind of concludes the fact that plasma p-tau 217 is able to distinguish between AD and other type of neurodegenerative disorders. And because I'm in the CIC lectures, meeting with neuroimagers here, here's some voxel-wise interaction exploring from the Prevent AD cohort. It's a manuscript in preparation by my colleague Fernando, showing an interaction between the plasma p-tau 217 rate of change in association with the amyloid PET rate of change and tau PET rate of change. And here we do see there are some widespread association with the amyloid and then more focal association in the temporal regions with tau PET. So PET imaging allows us to observe Alzheimer's disease pathology in living human, but the gold standard and the definitive diagnosis remain the neuropathological examination. So different studies wanted to investigate whether these markers could actually mirror what we see post-mortem at the post-mortem or autopsy. And this is a study came from using the Arizona neurodegenerative disease cohort. This is from the Swedish group as well, using anti-mortem plasma data with post-mortem data showing here on the ADNC scale, so the AD neuropathological change, taking into account both amyloid and tau load. And what we see here is that plasma A-beta ratio, it does actually differentiate between individuals with very much low pathology and neuropathological examination and intermediate pathology, but then it does not really differentiate between individuals at the different groups. While p-tau 217 assay marker actually could show differences between those with no pathology at all, those with very much lower pathology, and between the intermediate and the high group as well. Now let's look at the temporal sequence of the biomarker changes to understand better how these markers actually change over time. And how does this abnormality are compared to what we see with in individuals with very much subthreshold of amyloid PET pathology. So here on the left, we see the sequence of different plasma compared with the CSF p-tau 217 and other regions in the tau PET. So we started with the entorhinal region and the temporal, and then followed by the neocortical ROI regions. And what we see is that plasma and CSF 217 both actually begin to accumulate and start to increase when we have very much lower amyloid pathology detected on amyloid PET. So it does start to begin to increase very much in the subthreshold of amyloid PET. And then on the right, this is a study from assessing the differences in biomarkers values over the course of AD. And in this here, the authors analyzed the differences in plasma biomarkers based on the estimated years of onset. And what they found is actually plasma A-beta ratio began, and both plasma A-beta and p-tau 217, I will just focus on these two biomarkers, they tested several. They could actually begin to start even 20 years prior to the symptoms onset. The plasma A-beta ratio actually plateaued at some point, while there was a continuous linear increase in the plasma p-tau 217. Okay, so these promising results had led the NIA and with the Alzheimer Association to update their guidelines to include blood biomarkers in their stratifications for amyloid, tau, and neurodegeneration. And building on the ATN framework, we wanted to assess the clinical value of this framework actually by evaluating the prognostic utilities of these blood biomarkers, particularly those related to amyloid and tau. So the questions we asked: could we predict future cognitive impairment through blood biomarkers? Could they have similar performance to what we see on PET and CSF? Because indeed, 2 years ago, there was a study from the Prevent AD looking also at the clinical value of the ATN framework using PET imaging. So this is a study from alumni in the lab, Sherry Starkwer-Brown, looking at that individuals with both amyloid and tau positivity are actually 50% of them progressed from being cognitively unimpaired to become a mild cognitive impairment, as opposed to only 10% of those with no detected pathologies on PET. And when we followed up with them 3 years later, 100%, so all these who were classified as being amyloid positive and tau positive, are now progressed to mild cognitive impairment. Similar study came out from the Swedish group using the Prevent AD data, showing also a high risk of progression almost within 60 months in those with both amyloid and tau, opposed to those with no amyloid or tau at all. So our objectives of this paper was to assess the prognostic value of plasma p-tau217 in predicting the progression from cognitive impairment to MCI. And for the purpose of the study, we used the Prevent AD Prevent AD cohort, which consists, if you're not familiar with, individuals who were enrolled with family history. So they were cognitively unimpaired, but they have family history of the disease. And these were actually self-reported. And for the purpose of the study, we classified individuals, or we chose individuals who are cognitively unimpaired at the time of the biomarker measurements. They should have also at least almost 1 year of cognitive follow-up thereafter. And we tried to select the biomarkers within the same time frame. So what we in 2017, we had blood measurements for both A-beta ratio and p-tau217, the same for CSF, and amyloid and tau PET. MCI diagnosis was done at a multidisciplinary consensus meeting using only the cognitive profile of the patient. And this was done between my supervisor, Dr. Sylvia Villeneuve, in addition to other members in the Prevent AD research group, Dr. Maxime Montebleu, Dr. Simon Ducharme, and Dr. Maya Geddes, where they evaluate the patient based only on their cognitive symptoms, blinded to biomarkers such as PET, CSF, or any type of genetic information. And we use different sample size. So here we have different sample size where most of them came from the plasma, but we did repeat the analysis when using participants with these all common biomarkers, and the results were very similar. So here I'm presenting the full sample size. Overall, in the plasma group, we had around 28 who progressed to MCI. In the CSF, it was kind of similar, with 23%, was much higher in the PET group, although because the sample size was smaller. And what we did here, we stratified our participants based on their amyloid and tau status, and we first identified certain cutoffs for each of the plasma biomarkers, the CSF and the PET. And these cutoffs were either chosen from independent cohorts, if possible, or if not possible with the assay we're using, it was based on in-house cutoff. So what we found is actually that 76% of those with both classified as being amyloid and tau positive on the plasma became MCI, and as opposed to 20% with those with no pathology. Similar findings were also observed in the CSF. And what was more interesting actually is that even those who were amyloid negative, so they had were not considered as being amyloid positive with the plasma A-beta ratio or the CSF A-beta ratio, but tau positive progressed to MCI with 70%. The group was smaller, but still. And on PET, the sample size for the A+T+ group was actually very much smaller, but all of the participants who were considered to be amyloid positive, tau positive, actually were MCI. And then we did Cox proportional hazard models. It's a survival analysis to assess the effect of the amyloid and tau on the risk of progression. And what we found here in red are the individuals who were positive on amyloid and tau, and these had a very much a higher risk of progression. Almost within 7 years of follow-up, all of the participants who were considered to be positive became MCI, and they had very much a higher risk of progression. And this progression actually was very much higher in the PET group, so in those with both amyloid and tau in the PET sample. Similar findings were also observed here in this paper that was published just earlier this year using the PREVENT-AD data as part of this cohort. But then they only used plasma p-tau217, so they got rid of the amyloid and compared it to the PET directly they have no CSF sample. And they divided the participants into quartiles, so without using thresholds. They found those with the highest quartiles were at the higher risk of progression within 6 years of follow-up as opposed to those with the very much lowest quartiles. In this paper, then, they assessed the cognitive trajectory of these participants and using the PAC score. And here we see that those with the highest quartiles in quartile 4 in orange and on green showed very much a steeper slope opposed to those with very much the lowest quartiles. So the take-home message of my paper was that we do see there's an elevated risk in those who would be classified as being positive on amyloid and tau, whether we use plasma, CSF, and PET. And indeed, plasma is offering a very much strong inference here that will indicate future clinical progression. So we could use plasma biomarkers as a prognostic measure in the clinic. Beyond plasma clinical diagnostic potential and their prognostic utility, we wanted to know what is their longitudinal change over time. And looking at that will allow us to know how could we use blood biomarkers in the clinic. Do these markers change? We could measure someone as being positive in the first time point, they come back in a year later, oh, they're negative. So how do these markers actually change over time? But not only this, how do they change in different assays? We have now more than 30 platforms to measure the same thing. So, and these are 2 initiatives that came out from the Global Biomarker Consortium on the left and on the right from the ADNI-FNIH consortium, looking at the cross-sectional differences between association between different plasma biomarkers measured with different assays, as you can tell. In detecting amyloid pathology here in detecting CSF, and on the right, amyloid PET and tau PET. And we do see clear differences between the different assays measuring the same p-tau form. But for instance, we see here up in the C2N, this is a mass spectrometer-based assay, there's a highest diagnostic accuracy as opposed to the other Simoa-based assay. So we took advantage of this ADNI-FNIH data, and I'm working now in collaboration with Dr. Pichat Pinet. She was an alumni in this lab, in the Villeneuve lab, and she is now an assistant professor in Université de Montréal. So we grabbed this data and we asked 2 questions. How these longitudinal plasma biomarker change in 14 different assays over a 10-year follow-up period, and how well these plasma changes could predict subsequent amyloid PET positivity across all these different assays. So we used the ADNI cohort. So the participants were aged between 50 to 90 years old. Plasma and PET measurements were done within 1 year, so we're restricted to have them all within the same year window. Participants have at least 3 times of follow-up, and we clumped together both the cognitively unimpaired and the impaired participants. And what you see here in this chart, the different assay that measuring different biomarkers. So we had the A-beta ratio measured with 4 assay platforms, 2 different p-tau epitopes. I will focus only on the plasma p-tau217 for now, measured 4 different platforms as well. And then we also had the GFAP and NFL as other markers to measure neurodegeneration and neuroinflammation, measured with 2 different platforms. So first we asked, well, how do these markers change over time, over a 10-year follow-up? And here we stratified them. We looked at them on the whole group, so in green, and we stratified them based on their amyloid and tau PET status at baseline. So we grabbed the threshold that was suggested by the ADNI cohort, and we stratified our participants based on their first amyloid PET scan into positive or negative. And we extracted the slopes from the linear mix effect models here in the forest plot. And what we found, there was a stepwise increase in all these plasma biomarker assays in the p-tau217, regardless of the assay we're using. And we do see there is a change, a higher rate of change in those who are considered to be positive to start with in their amyloid PET scan. While we do see a decrease in the plasma A-beta ratio, while it's very much less subtle as opposed to the plasma p-tau217. And a decreased A-beta ratio means more abnormal. And then we looked at whether at their slope and how do they interact with, if there's an amyloid-dependent changes. And on red here, we see the amyloid PET positive group at baseline, and in blue, the amyloid PET negative group. And we do observe a higher slope in the amyloid PET positive participants over time across all these plasma p-tau217, regardless of the assay or the platform they were measured with. With the A-beta ratio, these were actually very much subtle. But we see plateau effect. There were some significant results that survived multiple comparisons, but there was a more plateau trend opposed to plasma p-tau217. And this was very much confirmed with previous findings over an 8 years period of follow-up using the BioFinder data from Nicholas Ashton group in 2022, also stratifying their participants based on their amyloid status, looking at the change and the slope differences between the different amyloid PET group in plasma p-tau217 here, and then the plasma A-beta ratio. This was done only in one assay, but it does confirm that we do see a steeper slope or a higher slope in the amyloid PET positive group at baseline over time in the plasma p-tau217, opposed to more plateau effect or no differences between the slope, the amyloid negative and the positive in the plasma A-beta ratio. Okay, and now we looked at the rate of change, but how do they change with amyloid PET? So we do have, we take advantage of the amyloid PET data, the long-term amyloid PET data available with ADNI. They also were available for almost 10 years of follow-up. And we did linear mixed effect models. We took the slope of both the amyloid PET and the plasma p-tau217 and stratified by their amyloid PET status at baseline. And we're starting to observe an opposite trend. So here we see a stronger association in those who are amyloid PET negative group. There's no more association in those who are considered already reached the amyloid PET positivity threshold. So what we did, we just looked at the raw data. And indeed, we see some nonlinear changes across the whole group in the plasma p-tau217 assays. So there was some of a plateau effect in the p-tau217. Maybe this is driven by the amyloid positive group, as we don't see these changes opposed to the amyloid PET negative group, where we start to see these changes more strongly. So we asked ourselves, well, do these long-chain changes also were the same at baseline? So we took the baseline data. So we started with the long-chain data, and then we wanted to know, is it the same as what we observe at baseline when we just do simple cross-sectional analysis? And we found an inverse effect. So at baseline, actually, it's the amyloid positive group that shows the best effect with amyloid PET opposed to the amyloid PET negative group. But when we looked at the long-chain data, there was an inverse effect where the amyloid PET negative participants start to accumulate more and start to show a better or an increase in their plasma p-tau217 levels. So this observe of nonlinear fit was very much similar to another study, it's cross-sectional study that was published last month, showing that plasma p-tau217 could actually, with the amyloid PET, once individuals are already reached their positivity threshold, there's no much changes in their plasma p-tau217 levels. And they did also the same thing for tau. And once those started already to accumulate tau, so once they are tau positive, there's not much change observed. So they do see some of this nonlinear trends in the plasma p-tau217 assays. Okay, so what's happening with those negative group? Who are they? They were negative at baseline. Are they progressing? So that's what we ask ourselves. And we found, while most of them actually remained negative across all the PET scans, amyloid PET scans, however, there were around 52 participants who were negative at baseline but became positive at the subsequent follow-ups. Okay, so what we did is we tried to investigate the risk of progression to amyloid positivity using Cox regression models, comparing the plasma rates of change and their baseline levels. And what we found in those amyloid PET negative group at baseline. And what we found here is that there was a higher probability of risk of progression from amyloid PET negative to amyloid PET positive within all these plasma p-tau217. It was very much higher when we looked at the C2N, which is the mass spectrometry-based assay, both at baseline and when we use the slope, as opposed to the other assays, while we do still see some changes. And when we repeated both the same analysis using the baseline plasma markers, higher plasma p-tau217 at baseline was also associated with a higher risk of progression to amyloid PET positivity. With the plasma A-beta ratio here below, actually the slope did not really show any differences in the risk of progression. There were, except maybe for the C2N assays, where we do still see some risk of progression to amyloid positivity when we use the slope. And at baseline, however, so when we use the plasma A-beta ratio at baseline concentrations, we do see that these were associated with the risk of progression to amyloid PET positivity. And here's an example, actually, classifying just of the survival curve, classifying participants based on their tertiles. And this is an example from the C2N. So we choose one from the mass spec assay and one from the Simoa-based assay for p-tau217. No, both, sorry. This is for p-tau217, this is for A-beta. And we found that those with the highest tertiles, this is in the slope, had actually progressed almost within 7 or 8 years, all of them to become amyloid PET positive. It was not the case for the slopes for the A-beta ratio. When we looked at the baseline, both those with the highest tertiles for the plasma p-tau217 showing a very much a high risk of progression, and those with the lowest tertiles or more abnormal plasma A-beta ratio at baseline showing the highest risk of progression to amyloid PET positivity. So overall, we did observe changes in the plasma p-tau217, which was not the case for the A-beta ratio assays. And this association was very much stronger in individuals who have not yet reached the amyloid PET positivity threshold. So moving along, well, here I'm just describing how we could use blood biomarkers in clinic, but what about their limitations? We do indeed have some limitations in blood biomarkers, and we cannot deny that neuroimagers will always have a big role to play in AD diagnosis. For instance, when we look at the heterogeneity and the different subtypes of AD, which is observed in later stages, it's only done with PET because of the spatial specificity, and this is not something that we could do with blood biomarkers. Treatment monitoring. So when we look at ARIA or amyloid-related imaging abnormalities here on MRI scan, this is only could be done with imaging tool. We cannot use blood biomarkers for that. And PET is often preferred for anti-tau targeting trials. So for anti-amyloid trials, maybe a plasma p-tau217 could serve as screening. For tau targeting trials, some trials are targeting more the tau aggregates, which can only be detected by PET. And finally, while it's very much important not to combine or exchange just both PET and biofluid together, because what we measure is very much different. So what we look at in the microtubule binding region with the tau aggregates on PET is truncated most of the time in the CSF and the blood. So what we look for always is in the N-terminal phosphoepitopes or the proline-rich regions. So they are not the same thing. What's next for blood biomarkers? So what I've been discussing mostly is individual biomarkers. There are now data showing, or more assays coming out, showing that we could actually look at proteomics, full proteomic data, more than 200 protein that could be measured with a single assay, with a blood drop, with the same blood drop. We put them in the, this is like Olink and ELISA assay, and we can detect measurements for more than 200 proteins. And in the future, actually, there are some preliminary results. Beside that, we could use finger prick. This is some work now being done in Sweden under Dr. Nicholas Ashton, showing that we can now do dry blood spots with blood data to be more accessible to rural communities. So we'll see what the future holds for that. And with that, I would like to thank everyone. And of course, many thanks to the Prevent AD participants, the ADNI participants, and without them, our research would not be possible. Thank you.
I think we have time for questions.
Thank you for the presentation. You showed one figure for rate of change in fit of someone else in the lab. But what about the actual fit, so not rate of change? So when you look at p-tau, any of them, like, is there a relationship?
Yes. So when we use the cross-sectional data, yes.
The same, do you have same visit or?
They are in the same, where blood often done actually a bit earlier than the PET, at least for the cross-sectional data, but we do try to take the measurements at the same time. This is with the rate of change. Yes, we did look at cross-sectional data, and the results were much actually similar as well. So even when we use the plasma p-tau217 at baseline with the amyloid and tau PET at baseline, the results were similar, at least also from what I know from other studies.
Similar to this maps? Or?
So it's more strongly with the amyloid rather than the tau, but when we look at the rate of change, it also depends, first on the group that we're looking at. So this is mostly the PREVENT AD, which tend to be younger and cognitively unimpaired. Now we have some progressors. It's more common in the amyloid. Yes, we do see there is more widespread within the amyloid than the tau with the plasma markers in general. Now we see also focal bindings with the tau rate of change.
Does the pattern make sense for the tau? It's a bit weird to me, the tau.
So we do expect with the tau to see binding starting with the temporal regions. I think here we're also seeing some in the occipital areas. Yes, this is very interesting because we do see some tau binding in the occipital in the PREVENT AD cohort. We are seeing this as well, not just with plasma. In general, when we're looking at scans, we do have some participants who have some focal bindings in their occipital lobe.
Thank you so much for the presentation. I have a question on the, actually, I found that slide on the economical impact. Like, interesting. I was wondering, how does it scale to when you, like, you didn't understand the amount, actually. So what does it represent, actually?
So this is the cost that it takes. So this is a hypothetical model. This is the cost it takes to start with an initial phone screen, doing screening visit and amyloid PET scan with the compensation and everything. This is the total cost, the estimate cost of how much would it cost for this number of participants to do all of these steps when including individuals with the clinical trials for screening. And this is the first model, actually, where we do initial like a phone call and then screening visits. So this is a neuropsychological examination, physical exam, and then they do amyloid PET to enroll in clinical trial. So now we're using amyloid PET as well. And this is how much it would cost. And the second approach is what would happen if we were to use blood tests after the screening visit. And based on that, we would determine if someone needs an amyloid scan or not. Would they be eligible? So I think that because that's the utility of blood biomarkers more in screening. And the third approach is we start with the blood even earlier before doing the screening visit. This could reduce the cost on the personnel and even the time. And the final approach is not even using amyloid PET. So just doing blood tests, and based on that, we enroll participants. We do, after the screening visit, we do enroll them if they are deemed eligible or not. 52, yes. Yeah. It's also worth keeping in mind, I think, with the different assays on what assays we could use, because some are more expensive than others. I always say that they are cost effective, but if we were to look, for instance, at the C2N or mass spectrometry assay, it could cost probably around $1,000. So the sensitive Simoa assays are probably cheaper, but if you want to be more specific, some assays could be on the expensive side. It's still very much cheaper, I assume, than PET, because with the PET tracers, it can cost up to $2,000, $3,000. Also, the waiting time is another thing. Yeah.
Could you just give us like a sense of like when you think that plateau effect happens in the disease control?
it's more in advance because this is a cohort with both cognitively unimpaired and unimpaired. So this is across the whole group. And here I have the shape based on their cognitive stages or the clinical stage. It is more observed in the later stages. When we look at the very much earlier stages, there was a linear trend. And I assume in the later, very much later advanced stages, there would be some plateau effect for this marker. There's not much studies actually what this nonlinear trend, because not much studies because we don't have yet, the ADNI was probably the first ones to have this kind of 10 years of follow-up. It's also the length of follow-up that matters. Often we look at follow-up for 4-6 years. So this is a very long follow-up looking at the participants from across the cognitive spectrum. And that's why we're observing this trend. There was another study that was looking at another marker, but that was published last year that looked at the same, found the same effect.
Yes,
in the later stages, yeah.
I think that I guess the use of 2017
Yes.
in these stages, in the later stages, and it's more like an early time.
It's a very interesting point. Yes, indeed. It's more used for early stages of the disease. Now there are work on stratification and disease staging as what we do with PET. And they found there are more forms of tau. The most recent one is the microtubule binding tau marker that was detected in the plasma. It's more used for later stages of the disease, opposed to the plasma p-tau217, which is still detecting the soluble forms that are very much still linked with the amyloid, which we know it's in the early stages of the disease. So the benefits of this marker could be used in screening individuals in prevention trials before having the dementia stage.
I have a question for the budget.
Mm.
How many people do you use?
It's not a.
So if you go to the
It's a hypothetical model. It's 152, and they missed 50 participants. So they started originally with around 400.
That's not what I'm saying. Like this is the whole model. So you have a plot that shows a correlation at minus 155. The quartile correlation.
This is not on the cost, or
not on the cost.
Okay.
Like, when you were showing the correlation.
The mass
Yeah. The plus. You have 4 quartiles. The up and up is empty, and you show a correlation of minus 0.5.
Okay. So that's for the plasma A beta.
Maybe. So that was my question.
Yes.
Yeah. So if we look at something similar to this for p-tau, we want to say, okay, if we look at the bottom part of this and we only go for those, or we go for only one of the quartiles, we miss these many subjects, or like essentially a question of sensitivity and specificity.
So this is so these are the thresholds.
Yeah.
Determined threshold for amyloid PET and the A-beta ratio, where we do know they start very much even. There's more abnormality because the lower, the more abnormal at the very much earlier stages before even being amyloid PET positive. We do observe there is a better plasma A-beta ratio was actually the earliest plasma marker, so I was just trying to put in history. With the plasma p-tau217, we do see a stronger correlation with the amyloid PET opposed to the A-beta ratio.
So if you do the same plot, you see much better.
It's a much stronger correlation, yes.
Okay.
Well, it would be here because like the higher tau, yeah.
Thank you all for coming, online, and thank you.
Thank you. Thanks for listening. Thank you so much.